Bismillahirrahmanirrahim. Today our lab is implementation of circuits of D flip-flop and JK flip-flop on Proteus. So the objectives of our lab is to know difference between combinational and sequential logic, and to have an understanding of flip-flops and design, and to practical knowledge and working of a positive edge triggered D flip-flop and positive edge triggered JK flip-flop. So first of all we have to know what are D flip-flop and JK flip-flop. So here is the D flip-flop. In SR NAND gate bistable circuit, the undefined input condition set equals to 0 and set equals to 0 is forbidden. So in SR flip-flop we have a one negative action, which is when set equals to 0 and reset equals to 0, then our flip-flop will behave unresponsive and it will give the no outputs on our table. So to remove this behavior of SR flip-flop, we make a D flip-flop. This is the block diagram of a D flip-flop, in which we have the inputs D, clock, and outputs Q and Q bar. So here is the truth table of D flip-flop. We have this input set, reset, D, clock, and outputs Q and Q bar. When the set is 0 and reset is 1, then whatever the D and clock is, we always get the outputs 1, 0. And when the set is 1 and reset is 0, then our outputs are 0 and 1. And when both set and reset becomes 1, then we will check the inputs D and clock. On the basis of that inputs, then we will get the outputs. For example, here when set is 1 and reset is also 1, then when D is 1 and clock is positive edge, then we get the outputs 1 and 0, and when D is 0, then we get the output 0 and 1. So here is the circuit diagram of a D flip-flop, in which you can see that we have first two NAND gates in which data input is, which is D input, and on the second NAND gate this D input becomes the inverter and then go to the NAND gate, and one is the clock input. And after that we have another NAND gates, for which one input is the previous outputs of NAND gates and one is the output of other NAND gate. So here is the circuit diagram of our D flip-flop. After that we have a JK flip-flop, in which we can see that the SR flip-flop or reset flip-flop lots of advantage, but it has the following switching problems. When set and reset inputs are set to 0, this condition is always avoided, because in this condition the SR flip-flop behaves unresponsive. So to remove that conditions, we made another flip-flop which is called JK flip-flop. So here is the block diagram of a JK flip-flop, in which we have 3 inputs J, K and clock, and 2 outputs Q and Q bar. After that we have the truth table of a JK flip-flop, in which you can see that we have the 3 inputs J, K and enable or clock, whatever it is, and outputs Q and Q bar. Whenever the clock is positive edge trigger or enable is 1, then our flip-flop be working, and when both inputs J and K are 0, 0, then our outputs remain same and we get the no change in the outputs. And when J is 0 and K is 1, so our Q is 0 and Q bar is 1, and that is called the reset state. And when J is 1, K is 0, then outputs are 1, 0, and that is called the set state. After that we have the circuit diagram of a JK flip-flop, in which you can see that we have 2 inputs J and K. The difference between JK flip-flop and D flip-flop is that in D flip-flop we have the one input in D NAND gate, which is D, and the other is inverter of D. But in JK flip-flop we have 2 other inputs which are called J and K, and the one input which is coming from the output of the other NAND gates. So these are the logics, circuits, block diagrams and truth tables of JK flip-flop and D flip-flop. Now we have to simulate them on Proteus. So here it is our procedure. After that we are going to move on Proteus. So here you can see that I have made the circuit of SR flip-flop, D flip-flop and JK flip-flops individually. I have already explained you the behavior and working of these flip-flops. Now when we run this circuit, first on the SR flip-flop, you see that when our S state is one high state and when our reset state is 0, because switch is open, so we will get the output Q is 1 and Q bar is 0. And after that you see that when I am going to S0 and R is 1, then you can see that our output is 0 and 1, Q is 0 and Q bar is 1. Now when I am going to give both inputs high, now you see that this is our unusual behavior of a SR flip-flop, because 1 1 is not acceptable in SR flip-flop, so we are going to avoid this inputs and we are going only 1 0 or 0 1 combination. Now in D flip-flop you see that we have made this D flip-flop to avoid this condition which is unusual in SR flip-flop, which is when both inputs are 1 1. So you see that in D flip-flop we have the first input D and the other input is invert of D. So whatever here is D switch open or close, we always get the two different inputs, because the second input is always the invert of first. So when our D is 1, switch is closed, so for this NAND gate the input is 1 and for this NAND gate the input is 0 and the other input is clock for both the NAND gates. So when D is 1 we will getting the output 1 and 0, and when the switch is open means D is 0, so we will getting the outputs 0 and 1. So by using this D flip-flop we can easily avoid this condition of SR flip-flop, which is unusual. Now coming towards the JK flip-flop, you say that I have made the circuit of a JK flip-flop in which we have the two input J and K. Now on the basis of that, you see that when J is 1 and K is 0, now we will getting the output 1 and 0, and when J is 0 and K is 1, we will getting the output Q0 and Q bar is 1. Similarly in SR flip-flop, when both inputs get 1, then you see that we are getting the invert of each other in outputs, which is called the toggle state. When Q is 0, Q bar is 1, and when Q bar is 1, Q is 0. This is called the toggle state when both the inputs J and K are 1 1. So these are our flip-flops that we see simulate on Proteus, and that's all for enough lab.